All right. So jumping back in here where we left off, we're gonna keep reading the ASM basics here, the help file for a little bit. Am I just gonna, basically read whatever this big long block of text is and regurgitate it in my own words? No, we're gonna diverge from this rather quickly, hopefully. But for now, we'll just, we'll read the introduction here. What are opcodes? An opcode, and also I don't believe in reinventing the wheel. If someone has explained a concept or done something in a really succinct, good way, proper way, then I'm not going to bother trying to one up them or anything like that. I'll just use what already exists. What are opcodes? An opcode is an instruction that the processor can understand. For example, sub, add, div. The sub instruction subtracts two numbers together. Most opcodes have operands. We talked a little bit about that in the previous video. Sub destination source, like the following: sub EAX ECX. Sub has two operands. In the case of a subtraction, a source and a destination, we talked about that and how they relate. Subtracts the source value to the destination value and then stores the result in the destination. You can see up here the source value is in fact the second one. It says it subtracts the source value to the destination value. If you want to be, a grammar Nazi, it should really be it subtracts the source value from the destination value and then stores the result in the destination. That's what it should really say. Operands can be of different types: registers, memory locations, immediate values. We'll talk, immediate values are essentially, in some really general way, they are literal values like 5 or 10. That's what we're going to call an immediate value. It's not necessarily true, but for our purposes here, that we're just going to, for us trying to learn what's really going on, we're going to say that we're going to define immediate values as literal values like 5. So basically that instruction is this. Say, for example, EAX contained 20 and ECX contained 10. EAX equals EAX minus ECX. What you're really saying is 20 minus 10. That's sort of the simple variable substitution we were messing around with in earlier. EAX equals 10. It's easy that bit, huh? Sure. Let's talk about registers. Here's the main force of assembly. Or let's read that again. Here's the main force of assembly. Registers contain values and information which is used in a program to keep track of things. And when new to assembly, it does look messy, but the system is practically efficient. It is, honestly. It is. It is really efficient to use registers. Let's take a look at the main register that's used, EAX. Say it contains the value FF, EE, DD, CC, H. The H means hexadecimal. You do not need to include the H, because when you're entering values in assembly, it's just implicit. When working later with soft dice, you will see hex values a lot. I don't know what he's saying there, but when working later with software, you will see hex values a lot, so get used to it now. I don't know. I'll show how the registers are constructed. We'll get to that. Floats, we'll get to that. All right. So let's see if we can recap what we just read in a somewhat, or let's see if we can recap sort of the previous two videos in a better way. We know what values are. We know what memory locations are. We know what variables are. And we know what pointers are. Let's talk about a register. How are we going to define this sort of elusive concept? Pretty simply, we're going to say that a register is a hardware variable. Period. End of sentence. I don't want to talk about it anymore. And yet I'm going to. Is that entirely accurate? No. It's not entirely accurate, because for a variety of reasons. But for our purposes, what we are going to assume, and for our purposes of writing assembly code, what we are going to say is that a register is a variable that has some location in memory. That memory may be, boot, or like screwed onto the processor in some manner of hardware architecture or whatever. But a register is a hardware provided variable, and we will expound on that in just a second. But let's just go over that again. What do we mean by this? What we mean by this is that we can put values in the variable, in the hardware provided variable, and then refer to whatever those values are by the name of the register. Well, that sounds simple enough, and it is simple enough. And the reason why we beat on the concept of variables earlier is because essentially the concept of variables grew from the concept of registers. There's some untruth to that, because you might say that registers grew from the concept of variables or variables grew from the concept of registers. I'm not super clear on it. I'll be totally honest that I'm not 100% sure on the history of the the chicken and egg between these two. But if you understand for how we have set up and talked about the series, we've talked about variables, or we talked about values, how variables have values, how variables have memory locations which have values, and so logically, when we're even though we're going lower in the hardware scheme of things, we can sort of draw some logical extension from what our conceptual understanding of a variable is to what our conceptual understanding of a register is going to be, and we are going to define our conceptual, or we're going to define the concept of a register as a hardware provided variable, and it is fast. It is ridiculously fast. We'll just say really fast because I don't feel like typing ridiculous. It's faster than RAM. It's faster than absolute memory. It's faster than pretty much any other thing on the machine. It's just really fast. So storing memories in a register, or storing values in a register and then doing operations on them, and then having results pushed into other registers or out into memory somewhere or something like that, that's the way you want to do it, because you probably can't make it any faster than that. And that's not a product of assembly language per se, or cheat engine certainly in any way. That's a product of how processors are designed and how registers function relative to processors. Processors have registers. There's sort of just these um, they're not all generic. You can't just go stuffing any single value or any random value into any random register. And we'll get into the different purposes of the registers in a little bit. But a processor has a set of registers associated with it. It expects certain values to be in those registers, and the hardware is designed from a microscopic level to be as fast as possible, and it enables us, using cheat engine and some of the assembly code and stuff here, to utilize those registers and push values in and out of them, and it all just happens extremely fast. I don't know any other way to say it than that. I'm not going to say, oh, we'll just go faster than the speed of light. Who the hell knows? I don't care whether it goes faster than C or not. And I don't mean C, the programming language, for the real geeky people out there. So, of course it doesn't go faster than C. But anyway, moving on. Let's talk a little bit about registers. Can we make this funny at all? Not really. Registers with a purpose. It's the worst Quentin Tarantino movie ever. So you have general purpose registers. We're going to glaze over this for now, and we'll jump into it in more detail in the probably the next video. But we have general purpose registers. We have we don't even need to type it out. At this point we can go back to the help file. Now that we've talked a little bit about conceptually what a register is. Do that. Opcodes registers. All right, let's let him do the talking for us. Registers contain values and information which is used in a program to keep track of things. It's kind of what we just said. Does look messy, system's efficient. We already went over that. Let's talk about how the registers are constructed. I don't want to get into the 32-bit, 16-bit stuff. So here we go. general purpose registers. These 32-bit and their 16-bit and 8-bit sub-registers, that's a distinction that we will glaze over for now, but again, something that we will get into. These 32-bit general purpose registers can be used for anything, but their main purpose is shown after them. EAX, and then in parentheses here is sort of highlighting the sub or the 16 and 8-bit registers that make up the extended 32-bit EAX register. But EAX accumulator, EBX base, ECX counter, EDX data. As said, these are hardly used nowadays for their main purpose, and what essentially this is saying is that you can stuff any random freaky value that you want into these 4 registers, and most modern programs will not care at all. Some will, and it's always good practice to store the value of these registers before you start pushing crazy stuff into them, and then restoring the value of whatever it was before you push crazy stuff into them after you're done pushing crazy stuff into them. So you store the value of the register before you mess with it, then you mess with it, and then you restore the original value after you're done messing with it. That's sort of the workflow, if you will, of how you manipulate these 4 general purpose registers. These are hardly used nowadays for their main purpose and are generally used to ferry around information within programs and games, such as scores, health value, etc., etc., etc. So does this mean that game developers are sitting around and they're writing code and saying, well, EAX is going to be the health value? That's not it at all. It's all sort of crazy automated in some ridiculous way, or in a lot of ridiculous ways. And believe it or not, there are compilers, interpreters, and things like that out there that sort of determine. You can give these things hints, you know what I mean? Like in C, I want to say that in C you have a register keyword, things like that. But in general, these are sort of determined on the fly, and they'll, be like, well, this looks like a generic value, so I'll stuff it in the AX. I mean, am I glazing over the details? Absolutely. But there is some sort of automated algorithms and whatnot that figure out this stuff and optimize code in such a way where generic values are probably stuffed in some of these uh, registers in order to make access faster. I want to say there's like a locality concerns. Let's talk about the segment registers here. The segment registers define the segment of memory that is used. We're not going to mess with any of that, so we're going to skip this. If you really want to know, you could read it, but you could also go to Wikipedia. You get a much more in-depth thing, but we're not going to worry about that. Pointer registers. You can use the pointer registers as general purpose registers except for EIP as long as you preserve their original values. Pointer registers are called pointer registers because they're often used for storing memory addresses, much as pointer variables, as we talked about. And pointer variables are just a rough analogy, or not even a rough, but they're just an analogy onto pointer registers. Just like general purpose registers as we define them are an analogy onto regular variables and software, again, as we defined them. So again, you're sort of seeing where we're starting to dig down deep enough where you're seeing the concepts that we were discussing and earlier in the series. How did they come up with these ideas? Well, they just were like, hey, this is how the processor is implemented, and it's great. It's really efficient when the processor is able to throw memory addresses around, so maybe we should make a variable that can throw memory addresses around and let software developers screw with that. It is a much more in-depth thing or process than my flippant sort of examination of it there, but essentially that's what happened. Some opcodes and also MOVB, some other thing, etc. use them. ESI, source index, EDI, EIP, and the main one that you will deal with when you're messing around with Cheat Engine in some sort of introductory way is ESI. What do we got? 25 seconds. EIP contains a pointer to the instruction the processor is about to execute. You can't use EIP as a general purpose register. Yep, you're never going to mess with EIP. So we'll pick this up in the next video.